All right, we looked at energy and water here today, so let's just review just a little bit and see what we got here. Okay, piezometers are open-ended tubes. They're used to measure pressure. The height of water rise in a piezometer is used to measure pressure. If you just have a tank with a couple piezometers in it, if no water is flowing, the water will rise to the level of the water in the tank. Okay. Now, if we have a tank out there somewhere in some town somewhere, we put a couple of piezometers in, which might be a little unrealistic to do, but let's just say we did that. And we have a closed valve. Again, the water will rise in the piezometers to the same height as the tank. Now, what's happening here is, let's say we got a 100-foot high tank, is we're going to get 43.3 psi down at the bottom here. That pressure will be present throughout that flat pipe there, but 43.3 psi is enough pressure to push the water back up to 100 feet. So what we're doing, we're transferring the energy from elevation to pressure, and then from pressure back to elevation. Now, if we look at a power hydro dam, okay, that generates power, what we're doing, we're moving energy through moving water through different forms of energy. We back the water up, and the water has elevation. It'll build up pressure down at a certain depth. That pressure will create velocity and push the water through a pipe that goes through the dam. If we put a generator in that pipe, we can use that velocity to turn the generator and generate electricity, which can power our lights at school. So what we're doing there, we're converting water into energy into different forms. Okay? In this case, elevation, pressure, and velocity. Now, these are called heads sometimes. So elevation head is measured as a vertical distance above a reference line, quite often called a datum. Our common datum, when you get surveyors out there working in a city, is sea level. We measure elevations above sea level. We can use any datum we want as long as we use the same datum throughout one particular analysis. Okay? Now, pressure head can do work through the forces it can exert, and velocity can do work through its energy of motion. Okay? These are all interconvertible. You can convert elevation to pressure, pressure to velocity, and then you could get pressure back on the other side if this dam had a backside to it with water in it, and that pressure could push the water back up to an elevation. So these forms of energy, or head as they're called, are somewhat interconvertible. Okay. Now, what we'd like to do is get a total amount of energy. The unit we use for that is feet. So what we would do here would be to convert the pressure and velocity into feet. That allows us to have one unit for all these forms of energy, so we can add them together and get a total. Okay, so elevation is already in feet. It's measured as a height above a datum. Pressure is measured in psi. If we multiply that by 2.31, we'll get that into feet. Velocity is a little funny. We take the square of the velocity divided by 2 times gravity. That can be derived using calculus and physics. Okay, so what we get there is the velocity squared over 64.4. That'll get us energy in feet. Now, the last form of energy is head loss. That's energy loss from a system. What that usually is friction that turns into a little bit of heat that just kind of dissipates into the atmosphere. That's the last form of energy that we'll analyze in water. It's different than the others, though, and then once you create head loss, you've lost that energy. You can't get it back. You can't convert it back into some other form of energy. Okay, so we went through this example here. If we have this pipe and we're looking at point A, and we know the pressure today is 100 psi and the velocity is 8.025 feet per second, we could find the total energy at A. Elevation head there is 200. 100 psi times 2.31 feet per psi is 231 feet. And the velocity squared over gravity, which is 64.4, or 2 times gravity, so velocity squared over 2 times gravity would be 8.025 squared over 64.4. Well, that works out to be 1 foot. Add those up, you get the total energy. That's 432 feet of total energy. All right. So the idea there, if you put a piezometer tube in this pipe and you measured the height that water rises above datum, it would rise up to 432 feet. That's the idea. So we're taking all the energy and converting it into elevation. Now, one thing I'd like to point out here is 8.025 feet per second is a very high velocity for a water system or a sewer system. It's rare to see velocities that high, but even with that high of a velocity, we only get 1 foot of velocity head. So the deal with that is that for this reason and for some other reasons too, we often ignore velocity head when we do calculations for everyday water systems because the velocity heads are just so small. They just don't make that much difference. They're a bit of work to calculate too, so they're often just ignored. All right, so we've looked at this tank with these piezometers in the pipe. What if we open the valve though? With the closed valve, the water rises to the same level as the tank, but if we open the valve, the water will drop a little bit. All right, now if we connect the dots there, we get something called a hydraulic grade line. So if we look at what the piezometer elevations would be anywhere along the pipe and connect the dots here, connect those elevations together, we get a hydraulic grade line. Okay. Now this can be used to model systems. In this case, it's modeling a sanitary sewer system. Now, being as we're looking at total energy by plotting up these piezometer elevations, what's going to happen with one of these is if the pipe bows down, let's say to cross some ditch here or something, the pressure is going to go up. Even though the water is dropping elevation, the corresponding pressure will rise as the water drops. The result is the hydraulic grade line won't dip like the pipe does. The hydraulic grade line will just have a steady sort of slope to it. This slope is really the head loss, the friction loss as the water flows. Okay, so even though the pipe might go up or down, the hydraulic grade line usually stays somewhat steady and has a downward slope that moves with the flow. The downward slope of the hydraulic grade line corresponds to the head loss in the water, the friction loss. So let's look at how we could calculate a hydraulic grade line. What I've got there is a pipeline plotted up. I've got elevations and I've got pressures that are measured at different points on the pipeline. Let's see if we can plot up a hydraulic grade line. Let's ignore elevation too. Okay. So what we want to do, and why don't you give this a run in your book, you've got spaces for points A, B, C, and D. Get the elevation head, that's just the elevation off the map. Convert the pressure into pressure head because we want everything in feet so we can add it together, and add those two things together and get the total head. And do that for all 4 of the points and then plot them up. You get the hydraulic grade line. Okay. So you could maybe pause the recording here and then do that and then see how your answer compares to what I'll show you here in just a second. All right, let's have a look. Okay, the first one there, we got an elevation head of 150 feet. Pressure is 20 psi. Convert that into feet though. What you want to do, you want pressure head there. You get 46.2 and add the two together, you get 196.2. The next one, we got 110 feet for the elevation, 30 psi for the pressure times 2.31 feet per psi, that's 69.3. Add that to the 110, we get 179.3. Here we've got the pipe dropping down to 60 feet. The pressure goes up to 48. Convert that into feet, that's 110.9. Add that to 60, you get 170.9. And then the last one is at 140 feet. 10 psi, convert that into pressure head, you get 23.1. Add that to the 140, you get 163.1 feet. So what you can do to get your hydraulic grade line is add those elevations to the existing elevations on the pipe, connect the dots, and you get that hydraulic grade line. Kind of a smooth line working its way to the right, dropping a little bit as it corresponds to head loss there. Okay. So there's a map of the system. Now this is an article from the Pacific Northwest Clean Water Association Journal, 8 years ago or so. And you can see how they're using this. Now they have some concerns here. They're mapping up a sewer system. Here's their map. They get like an aerial photo and put their manholes on here. And then they look at what happens with the flow if they have a big storm. This is a storm drain. Okay, they got a little problem here because their hydraulic grade line is above the surface of the ground. What that's going to do is that's going to push water through that pipe, and then the water is going to push up through the manhole. And if this actually happens, the water is going to push up right up through the manhole and start flooding the street. Okay, so that's one of the uses of a hydraulic grade line. It allows you to visualize where the water would be in a system. Okay. Now let's have a look at Bernoulli's equation. This is an equation that was developed back in the Renaissance by a scientist named Bernoulli from a famous family of scientists. And this scientist here analyzed energy in water. He came up with this equation here, that if you look at your initial energy, elevation, pressure, and water, subtract off the head loss as you flow to a second point, that will equal the final energy, elevation, pressure head, and velocity head. So I might have misspoke there. We got elevation head, pressure head, and velocity head on the left. Subtract off the head loss, and we get elevation head, pressure head, and velocity head on the right. We can use this to analyze hydraulic systems, pipelines, and things. So let's go back to that same problem we were looking at, where we have information about point A. We've got the velocity at A, we've got the pressure at A, and the elevation at A is given. Let's say also that we know the head loss from A to B is 20 feet. Now we'll work out how to find head loss later, but for right now I'll just give it to you. So I'm saying the head loss from A to B is 20 feet. If point B is at 120 feet elevation, what's the pressure at B? What would we predict that to be? Okay, if we got a little pressure gauge there, what would we predict the pressure at B to end up being? Okay, let's have a look. Now what we want to do at A is add up the different forms of energy. Okay, and we've already done that. We did that earlier on. And all right, there we go. There's the energy at A. 200 feet for elevation, 100 psi, which is 231 feet of pressure head, and 1 foot of velocity head. The total energy at A is 432 feet. Now, we know we've got head loss. As we move to B, so let's see what happens at B. Okay. So what we've got going on there is we can figure out what's happening at B if we consider the head loss. Now I like to put this stuff in a chart, something like that. So I want A and B for columns, a head loss column in the middle, and then I just want rows for elevation head, pressure head, velocity head, and the total. I'll just fill them in. This makes it easy for me to organize the information. Everything that goes in the chart should be in feet of head. So at A, as I just showed you there, we've got 200 feet for elevation, 231 for pressure, and 1 foot for velocity. Total then is 432. Okay. Now we got 20 feet of head loss from A to B. So that's going to take our available energy and bring it down to 412. So we lost energy as the water flows from A to B because we have friction loss. Okay. So this flow of water involves some friction loss, so we get energy loss from A to B. So we only got 412 feet available at B. Now the elevation's 120. We're given that. Now we've got one size of pipe from A to B, so the velocity should stay the same. And if the velocity stays the same, so should the velocity head. So that's a foot. Okay. So what we got is we got a total of 412. We're going to use up 120 for elevation and 1 foot for velocity. So 412 minus 120 minus 1 is 291 feet of energy available for pressure. That's what's available for pressure. We're using up 120 for elevation. We're using up 1 for velocity head. So we've got 291 left for pressure. We can then, now that's feet because it's on the chart. So we can convert that into pressure and get 126 psi. So that's what I would predict the pressure at B to be, 126 psi. Okay. Now this is a nice method for analyzing pipes and hydraulic systems. We just track the energy in different locations with a chart and look at the head loss from one point to the next. So we get the total energy here at 432 at A. Once we've got that, we can take away the 20 feet of head loss, and that'll be 412 feet. We know we've got 120 of elevation head at B and 1 foot of velocity head at B. Subtract those from the 412, we get 291. We can then convert that into pressure, it's 126. Now I think of this a little bit like accounting in a way. I've got different bank accounts here for elevation, pressure, and velocity. So, and I can just move money between the accounts, but I can also track the total amount that I've got. So at A, I've got 200, 231, and 1. The total is 432. Then let's say I spend 20 feet, so to speak, $20, 20 feet, whatever. That means my total left over is 412. I know I've got to have 120 in the elevation account. I know I've got to have 1 in the velocity account, velocity head account, I guess. So that leaves 291 left over for the pressure head account. Now that's in feet, so I can convert that into PSI. Okay. So that's how I approach those. Okay, once you have a look at this one, we've got a reservoir there with an open reservoir, elevation at 497. We're going to flow water down to a hydrant at 401 feet. Head loss will be 24 feet in that pipe. Let's find the pressure at the hydrant. Okay, now what we got here is an open reservoir. That's open right there. So that means the pressure up there is going to be 0 at an open reservoir. Okay, that's going to be 0. So once you fill in that chart and find the pressure at the hydrant, you can pause the recording when you do it, and then after you're done, start it up again and we'll go through it. All right, here we go. We got our table set up like that. Reservoir on the left, head loss in the middle, hydrant on the right. We'll fill in the reservoir first. All we got there is 497 feet. We're ignoring velocity head. I forgot to mention that, but that's in the problem statement. It's often ignored. It's often not a real big deal, so we ignore it. So we're just not going to consider that. It's not very high. We're just going to ignore it. So we get 497 feet of total energy at the reservoir. We're given the head loss at 24, so we got 473 left over at the hydrant. The hydrant has an elevation of 401. So 473 minus 401 gets us 72 feet of energy available at the hydrant. We can then convert that using the 0.433 and we get 31.2 psi at the hydrant. Right, so there's some Bernoulli's equation applications. Using the table, you can just plug everything in. Remember, everything that goes to the table is in feet. So everything you're putting in the table is in feet. You get it off the table, it's in feet. You can then convert it into whatever unit you want to work with. Okay.